Let's spend a few minutes discussing esters. We make esters typically from carboxylic acids. As we saw a few videos ago, we can make them from the carboxylic acid chloride or the acid anhydride as well. So we have several options here. One that we have not yet discussed is a couple options from the acid itself. First one would be a two-step process where the first step involves deprotonation of the carboxylic acid, making a decent nucleophile. Reacting that with a good electrophile, such as methyl chloride or ethyl chloride, would allow us basically to alkylate the oxygen. And so that, via a simple SN2 process, would allow us to alkylate the oxygen. You can do that with probably any primary alkyl halide you want to. Another option would be to use acidic conditions. And I'm just going to show generic ethanol here. Draw sulfuric acid in a way that I can show a good mechanism. And the product is the ester, the ethyl ester, plus water. So we're going to remove the O and the H, and that makes water. And we're going to combine the O-ethyl from the ethanol with our carboxylic acid. So this is called Fissure Esterification. The mechanism is well laid out in your book, but I'm going to show that here. This is a fun with acid problem, as you hopefully noticed from me drawing sulfuric acid as the catalyst. So the first thing you should do is to protonate your electrophile and make it a better electrophile. Every reaction step in this reaction will be reversible, and that is typical of most fun with acid problems. And now we're going to have our nucleophilic attack step, making the tetrahedral intermediate. We formed a better electrophile by protonating it, so our weak nucleophile can attack. And if I don't draw reversible arrows, I meant to, so you can go back and fix that for me. And now we need to do a proton transfer step to get this hydrogen off of the one O and onto the other O. We know that we want to make water, so we better protonate one of these OHs. You could just draw a one-step sequence to transfer this proton, but in reality it is a two-step sequence, so it's better to draw it in two steps. It takes a little more time. And I made a protonated ethanol, basically. I want to show that this hydrogen is available for transfer. Another proton transfer to protonate one of the OH groups. That allows me to have water as a leaving group. I can reform the carbonyl now, losing a new leaving group. This is a loss of leaving group. This is one of the few non-proton transfer steps. You can see that we've gotten very close to our expected product. We just have this protonated ester now, and I'm going to draw my two arrow push proton transfer as the final step. So this is Fissure Esterification. It is several steps, most of which are proton transfers. There's of course the nucleophilic attack using the ethanol, and there's loss of the water byproduct. You can review this mechanism in more detail if you need to in your textbook. I would like to point out that if you examine all the different intermediates here, there are no anions that I've drawn whatsoever. This is a fun with acid problem. This sulfuric acid protonates things. It has no more role to play. So we've gotten our extra proton. Now we have a bunch of cations present. Here's the cation, here's the cation, there's our cation, cation, cation. And that's what's going to happen in this fun with acid problem. Do not use any bases, any strong bases. Do not form any O minuses. All steps are reversible here, and so a chemist can influence the outcome of this reaction by removing the water as it is formed, or distilling off the lower boiling ester as it's formed. Removing either one of these will use Le Chatelier's principle to drive the reaction towards the products. As we said before, we could also use the acid chloride to do the same thing. It's a little simpler mechanism. Sometimes it's an easier reaction to occur. But again, once we're in the lab, in the pot, just because I drew 7 steps to my Fissure esterification mechanism, that does not mean it is a more challenging mechanism to produce in the laboratory environment. That just means there's more intermediate steps. Proton transfers are extremely fast, and so that is not necessarily a good argument to use the acid chloride. Maybe you just have an acid chloride sitting around, or you've made it and it's sometimes an easier reaction. We don't have to heat it as long. We don't necessarily need to affect the outcome using Le Chatelier's principle because it's mostly downhill. High energy to low energy makes it a little easier to use that reaction. All right, another reaction of esters is saponification. And that's where we take the ester, react it with sodium hydroxide or some other base as the first step. Second step is work up with mild acid. As you might expect from our study of nucleophilic acyl substitutions, we've got a decent nucleophile. We are not in acidic conditions, so we should take the nucleophile and attack the electrophile right off the bat. I've made an anion in this case because I started with an anion in my base, so this is perfectly reasonable. The next step is reforming the carbonyl, and we'll lose the other leaving group that we could lose in this case, which would be the O, or the ethoxide. And so the next step is actually going to be deprotonation of our newly formed acidic hydrogen. There's no way to prevent this because as soon as that ethoxide forms, it is right in close proximity to our newly formed acidic hydrogen. So this step is unavoidable, and that results in the carboxylate being formed with our protonated alcohol. That's where the second step is important. We add mild acid just to protonate this O and produce our desired neutral carboxylate product. So mild acid just provides a proton in this proton transfer step. So that's called saponification. You can read more about that in your textbook. Saponification was used in the 1800s, 1700s as a means of making soap. Fat is made out of esters, and we can saponify the fat in order to make soap. So you can read more about that in your textbook. Another option is the acid catalyzed hydrolysis of esters. And actually, let me modify this ester. I want it to look just like the ester that I used in the Fissure esterification. So basically, in this case, we are taking the ester, hydrolyzing this bond. We're adding water across this bond. Here's the OH from the water. Here's the H. We've broken the O-ethyl portion of the bond. And this is, let's label this acid catalyzed hydrolysis. It's the exact opposite of what we saw a few slides ago, Fissure esterification. So if you take the 7 or so steps that we used in the Fissure esterification mechanism, reverse all of them, that is the mechanism for this acid catalyzed hydrolysis. So I'm not going to show that mechanism here. You can check that in your book, but it is exactly the opposite. Every step just in reverse of the Fissure esterification reaction. One very useful reaction is converting esters to aldehydes. And we can do that with a special hydride agent, reducing agent, different from what we used for acid chlorides, but still the same concept. Diisobutyl aluminum hydride, followed by water or mild acid workup, will add a single hydride, removing the OR group of the ester and giving us the aldehyde. So diisobutyl aluminum hydride looks like this. We've got an aluminum, we've got a hydride, and we have 2 R groups. Those are isobutyl groups. So diisobutyl aluminum hydride basically adds only one hydride. It does not react with aldehydes. Remember, the problem with lithium aluminum hydride is that we take the ester straight to the primary alcohol. And if we want to stop at the aldehyde, there's no way to do that with lithium aluminum hydride. So we use this tempered, moderated hydride reducing agent. It adds only one hydrogen to our carbonyl. And lastly, aside from lithium aluminum hydride, esters and Grignard, we saw this in lab as well, so I'm not going to spend too much time on this. But of course, if we have a random ester, we can add 2 Grignard reagents to that, follow that up with mild acid, and we end up with the tertiary alcohol, where we've added 2 Grignard reagents to our ester. We saw this in lab. We know that Grignards add twice to esters, and so you can look up that mechanism both in the alcohol chapter and in this chapter.